The joke that Muslims actually discovered the rocket but could not send it into space has been told since I was a child. Although very famous and advanced astronomers were trained in the Islamic geography 800, 900 years ago, it is certain that they have not advanced in the field of space today. I would like to get to the point without speculating too much on this issue. A great simulation of the forces acting on a rocket during its launch. How thrust, time of thrust, and mass of a rocket can be changed to make a rocket go as high as possible. How drag influences the height reached by a rocket. How the speed and forces acting on a rocket change during a launch. How the changing mass of a rocket affects the speed and height of a rocket. I will be leaving the link to this great rocket simulation in the description. So, we're supposed to be able to go 400 kilometers in the simulation. In this way, you can try it yourself and see more clearly how which value affects the height of the rocket. A rocket will launch and keep speeding up as long as the force pushing it upwards, thrust, is greater than the forces pulling and pushing it downwards, gravity and drag. There are 4 major components to any full-scale rocket: the structural system, or frame, the payload system, the guidance system, and the propulsion system. The propulsion of a rocket includes all of the parts which make up the rocket engine: the tank's pumps, propellants, powerhead, and rocket nozzle. Thrust is the force which moves a rocket through the air and through space. Thrust is generated by the propulsion system of the rocket, just like in a jetpack. Different propulsion systems develop thrust in different ways, but all thrust is generated through some application of Newton's third law of motion. His third law states that for every action, force in nature, there is an equal and opposite reaction. Just like in our daily lives, if object A exerts a force on object B also exerts an equal and opposite force on object A. In a rocket engine, fuel and a source of oxygen called an oxidizer are mixed and exploded in a combustion chamber. For a rocket, the accelerated gas or working fluid is the hot exhaust produced during combustion. This is a different working fluid than you find in a gas turbine engine or propeller-powered aircraft. Turbine engines and propellers use air from the atmosphere as the working fluid, but rockets use the combustion exhaust gases. In outer space, there is no atmosphere, so turbines and propellers cannot work there. This explains why a rocket works in space, but a turbine engine or a propeller does not work. Newton's first law helps us understand how forces get objects such as rockets moving. So, every object will remain at rest or in uniform motion in a straight line, unless compelled to change its state by the action of an external force. A modern heavy space booster has a takeoff thrust of 3,800 kilonewtons, 850,000 pounds. An object at rest, not moving, will remain at rest unless acted on by an unbalanced force. Also, an object in motion will continue to move at a constant speed in a straight line unless acted on by an unbalanced force. When a rocket is sitting on the launch pad and not moving, there are forces acting on it, but these forces are balanced. This means that the force pulling it downwards, gravity, is equal to the force pushing it upwards, support force of the ground. These forces are balanced. The rocket will keep on not moving, as described by Newton's first law. There are 2 forces acting on a rocket at the moment of liftoff. Thrust pushes the rocket upwards by pushing gases downwards in the opposite direction. Weight is the force due to gravity pulling the rocket downwards towards the center of the Earth. For every kilogram of mass, there is 9.8 newtons, N, of weight. As the rocket increases speed, there is a third force of drag that begins to increase. The resultant force is the sum of these individual forces. As an example, think of a rocket with a mass of 10 kilograms. The force of gravity pulling it downwards is 10 x 9.8, which equals 98 N. To get the rocket off the launch pad, the thrust must be greater than 98 N. For example, if the thrust is 120 N, the resultant force is 120/98 equals sine 22 N upwards. The Apollo 11 mission to the moon was launched in 1969 by a Saturn V rocket. The height of the rocket was 111 meters, longer than a rugby field. The diameter at the widest part was over 10 m, about the length of a classroom. The total mass of the rocket was nearly 3,000 tons, which is about the same as the mass of 417 school buses. To launch this enormous rocket off the ground, NASA used 5 F-1 rocket engines, the most powerful rocket engines ever flown. The thrust needed to be greater than the weight force of nearly 28,700,000 Newton. The engines produced a thrust at liftoff of 33,400,000 N, enough to lift 487 school buses. This means that the resultant force was about 5,300,000 N upwards. In addition, let's look at how much G-force acts on the astronauts during takeoff. The G-force is a measure of how much force acts on a person or an object compared with the normal weight force due to the Earth's gravity. To calculate G-force, divide the resultant force by the weight. This means that at liftoff, the Apollo astronauts experienced 1.8 G, nearly twice the normal force due to gravity. The Space Shuttle main engine operates at greater temperature extremes than any mechanical system in common use today. At minus 423 degrees Fahrenheit, minus 252.7 degrees Celsius, the engine's fuel, liquefied hydrogen, is the second coldest liquid on Earth. Meanwhile, the coldest liquid is liquid helium, with minus 452 degrees Fahrenheit. When it and the liquid oxygen are combined and combusted, the temperature in the main combustion chamber is 6,000 degrees Fahrenheit, hotter than the boiling point of iron. The energy released by the 3 Space Shuttle main engines at their full power, calculated in watts, is equivalent to the same amount of energy created by 13 Hoover dams. At this point, I would like to give additional information. Hoover Dam is a concrete arch gravity dam in the Black Canyon of the Colorado River, on the border between the U.S. states of Nevada and Arizona. By the way, let's get back to our topic. The Space Shuttle main engine fuel turbo pump weighs about the same as a V8 automobile engine, but develops 310 times the brake horsepower and develops as much torque as 18 V8 auto engines. The main shaft of the turbo pump rotates at 37,000 RPM. A car operating at 60 miles per hour runs at 2,000 revolutions per minute. One Space Shuttle main engine generates enough thrust to maintain the flight of 2.5 Boeing 747s. Even though a Space Shuttle main engine weighs 1/7 as much as a locomotive engine, its high-pressure fuel pump alone delivers as much horsepower as 28 locomotives, while its high-pressure oxidizer pump delivers the equivalent horsepower of an additional 11 locomotives. The maximum equivalent horsepower developed by the 3 main engines is more than 37 million horsepower. The combined volume of the external tank's liquid hydrogen and liquid oxygen tanks is 73,600 cubic feet, equal to the volume of nearly 6,600 square-foot homes. The 2 solid rocket boosters generate a combined thrust of 5.3 million pounds, equivalent to 44 million horsepower, or 14,700 six-axle diesel locomotives or 400,000 subcompact cars. At liftoff, the 2 solid rocket boosters consume 11,000 pounds of fuel per second. That's 2 million times the rate at which fuel is burned by the average family car. At 149.2 feet tall, the solid rocket booster is only 2 feet shorter than the Statue of Liberty. But each 700-ton loaded booster weighs more than 3 times as much as the famous statue. If you like the video, please subscribe my channel and do not forget to like. Please stay tuned to watch similar videos. Thanks for watching.